Hello, I welcome you all to this another interesting screencast. The problem reads a radar gun at O, which is the reference, rotates with an angular velocity of theta dot equal to zero point 0.1 rads per second and angular acceleration of theta double dot equal to 0.025 rads per second squared at the instant theta equal to 45 degrees as it follows the motion of the car traveling along the circular road having a radius of r equal to 200 meters. Determine the magnitudes of velocity and acceleration of the car at this instant. This problem is coming from the Engineering Mechanics and Dynamics 14th edition by RSC Hibbeler. Just a quick reminder, velocity is a time derivative of position and acceleration is time derivative of velocity. From the two equations, we have this derived equation v dv like so. From these three kinematic equations, we are able to derive a couple of equations depending on the boundary condition. But we do have one common set of equations that we usually use when acceleration is constant at t equal to 0. We have additional boundary condition S naught and V naught. And from this boundary condition, we can derive the following: S equal to S naught, V naught plus half AC t squared. V equal to V naught plus ACT and V squared equal to V naught squared plus 2AC S minus S naught. Right. So let's look at what we are now dealing with. Here we have a radar gun at O. This is our reference. And this radar gun rotates with the angular velocity given 0.1 rads per second and angular acceleration of 0.25 rads per second squared as it follows the motion of the car traveling along a circular road having a radius of r equal to 200 meters. And we've been asked to find the magnitudes of velocity and acceleration. Remember, in the previous problems, we are using tangential and normal reference system, right? Remember, we had tangential and normal reference system. In this particular problem, we are using r and theta coordinate system, or the polar coordinates, right? But we find that the solutions that we're going to find here will not be different from the solutions that we can find using the normal and the tangential coordinates. Okay. Right, so let's show these coordinates. So we have one coordinates designated as positive, okay, along the radius, okay, like so, and then another one which is perpendicular or tangent to the curve. All right, so let's call this one is our r and positive r, and then this one as our theta. Okay, there we go. Right, so let's find and if you remember we had called this one as our normal. Remember, right? We had called this one in the previous case. Remember, right? We had called this is our normal. Okay, let me also draw some arrows there. This is our positive and this is our positive. Remember this? Okay, and we had also, I'm just trying to show this. Okay, I'm just trying to show this. Remember this, right? Okay, we had something like this and we called this as our normal coordinate, right? And this one as our tangential coordinate, right? I just want to include them there also. All right, so we are using the polar coordinates now. So we want to find our velocity and okay, so let's start. So we know that our v expressed as a vector is equal to vr, okay, by the unit vector in that direction, and v theta by the unit vector in that direction, right? And we know to say our vr itself is just r dot, and our v theta itself is just r theta dot. And then we do have our acceleration, which is just equal to ar UR like so, okay, plus A theta U theta like so. Okay, and our AR is equal to R double dot minus R theta dot squared. And our A theta is just equal to R double dot theta double dot plus 2 R dot theta dot. You can check out on how to derive this. Right, so we know that our R is equal to 200 meters and is constant, and therefore our R dot, and this R dot is just equal to the R dt, right? Okay, so R dot itself is equal to 0 since R is a constant, and R double dot is also equal to 0. And then theta dot we have already been given, okay, it's just 0.1, and theta double dot is 0.025 also given. So let's now begin to replace these just as following mechanical steps, because we have everything that we need. So therefore our VR, okay, which is just equal to R dot is equal to 0, okay, and our V theta is just equal to R, okay, theta, which is just equal to 200 by 0.1. Therefore our theta, or V theta, our V theta is just going to be equal to a 20, right? Okay, it's a 20. Okay, that's a 20. That's 200 by 0.1. That's a 20. All right, so we're done with the first step, and then let's go to AR. Oh no, we are not yet done. Let's find the magnitude. So our magnitude, since VR is equal to 0, therefore our V, okay, it's just going to be equal to V theta, which is equal to, as in the magnitude itself, 20, what are the units, meters per second. So this is the magnitude of our velocity, and this velocity is also, we can also write this V theta, okay, is just equal to, if you remember, to V tangential, right, which is equal to 20 meters per second. Okay, great. So we are done with the first step. Let's go to the second step so that we find, so this is the velocity at which our car is moving, that is being monitored by this radar gun. Right. So let's move on to the next step. Our next step is we have AR, which is just equal to R double dot minus R theta squared. Okay, and therefore this is just going to be equal to 0 minus what is this? R is a 200, and then this is 0.1 squared. Okay. AR is equal to minus 2, and therefore AR is also equal to minus AN, which is just equal to minus 2. Remember this? Because they are in the opposite direction, but of course that's a centripetal, right? So let's go to the next step, which is A theta equal to R theta double dot plus 2 R theta R dot, and times theta dot. This is equal to a 200 by 0.25 plus 2 by 0 by 0.01. Of course, this whole part goes to 0. And therefore, this just becomes equal to, that's 200 by 0.25, and this is a 5. And our A is just going to be equal to square root of AR squared plus A theta squared. And our A is just going to be equal to, that's 2 squared plus 5 squared. Square root of that, we just get 5.39 meters per second square. I guess we are done. We have found the magnitude of our velocity at which this particular car is moving. Okay, and we've also found the acceleration at which this car is accelerating. So I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screen.